this lecture we calculate moments and products of inertia of some simple geometric figures. To start with, let us take a square of side A and calculate the moment of area and product of area of the square. The side is A. Let this be the x axis and let this be the y axis. Now, you recall that Ixx, that is the moment of area y square dA, which indicates that I take a small infinitesimal area here and its distance y from here, multiply by y square dA and integrate. Now, in this case dA happens to be very simple, that is the infinitesimal area dA is nothing but dx times dy, and therefore Ixx is going to be equal to y square dy, and this varies from minus a by 2 to a by 2 times dx, which varies from minus a by 2 to a by 2, and this comes out to be a, this integral gives you a times 1 over 3 y cubed varying from minus a by 2 to a by 2, which is nothing but a by 3 a cubed by 8 times 2, which is a raised to 4 divided by 12, because this gives you 4 here. Similarly, since it is very symmetrical, Iyy, let me write in a different color, Iyy will be equal to x square dA. So, what I will be doing is taking this area dA and multiplying it by x square. So, this will become integral x square dx minus a by 2 to a by 2 times dy minus a by 2 to a by 2, exactly the same integral as in Ixx, and therefore, I get a raised to 4 by 12 here too. How about the product? If I were to calculate the product of inertia of this, product of area of this square, then Ixy is nothing but integral x y dA, which is integral x dx y dy, and both vary from minus a by 2 to a by 2, minus a by 2 to a by 2. This being an odd integral and integrand and going from minus a by 2 to a by 2, this becomes 0. So, for a square, if I calculate the product of area with the product of area and moment, the second moment of area, this is in a coordinate system with the origin at the center of the square, we get Ixx equals Iyy equals a square over 12 and Ixy to be 0. Recall, in the previous lectures what we have learnt is that in the principal axis Ixy is 0, and therefore, these axes shown here are the principal axes for this. Also notice in this case that you have tangent 2 alpha is equal to 2 I x y over I y y minus I x x, and this in this case comes out to be 0 by 0. That means I could take any alpha and the axis would be principal axis. Therefore, in a square, any axis at any angle could be this, could be this, all these are principal axis. If the originally chosen xy axis were the principal axis alone, then this would have come out to be 0. Okay, problem number 2. I wish to calculate the moment of area, second moment of area and product of area of a square of side A with one of the corners at the origin. So, this is x, this is y. So, I could calculate this very easily from the result of the previous problem, but I will do it explicitly so that you see it how these calculations are done, you get some practice. So, again I x x is equal to integral y square dA. dA is this small area and this is the distance y. So, in this case this will become y square dy, y varies from 0 to a and dx which varies from 0 to a. The limits are from this point to this point, and this becomes a cubed over 3 times a, which is a raised to 4 over 3. Exactly the same distances are involved in calculating IYY. So, IYY, which is equal to x square dA, would also give you a raised to 4 over 3. How could I have gotten the same result from the previous problem? Just to find the relationship, remember in the previous problem I had a square like this and this side was a, and in this case IXX, which is actually measuring y square times dA, was equal to a raised to 4 over 12. If I take this side to be b, then a is to b. So, this I can also write as 2 raised to 4 times b raised to 4 over 12, which is equal to 16 b raised to 4 over 12, which is 4 b raised to 4 over 12. Right. So, if the side is b, this half side is b, I get 4 b raised to 4 over 12 as the second moment of area. But notice y square is same for all these 4 areas. So, all these 4 areas contribute equal to IXX, and this implies if I were to calculate IXX only for this, it will be 1/4 of whatever I have calculated. So, IXX for the quarter shown shaded, the answer will be b raised to 4 over 12, and that is exactly, oh I am sorry, this is 3 out here, b raised to 4 over 3, and which is the same as the earlier answer. So, you could also relate, and this also gives you some practice as to how to think if the shapes are similar. More interesting in this case, however, would be to calculate the product of area of this square 0 to a. Product of area is equal to integral x y dy. So, if I take this small area out here, this is integral x y dx dy, which I can write as x dx 0 to a integral 0 to a y dy, which comes out to be a square over 2 times a square over 2, which is a raised to 4 over 4. Now, if I were to find the principal axis, remember we had the formula tangent to alpha equals 2 I x y over I y y minus I x x, where tangent to alpha is the tangent of this angle alpha through which I have to rotate the axis to find the principal axis. So, this comes out to be 2 times a raised to 4 over 4 divided by 0, which is infinity, and this implies 2 alpha is 90 degrees or alpha is 45 degrees. So, we find that the principal axis in this case is going to be at 45 degrees to the x axis, and therefore, this is the principal axis. In this I x y, in this new set of axes, let us call it x prime y prime, I x prime y prime will be 0. Next, I solve the problem of finding the product of area for a semi-circular disc. I will take this disc with the center at the origin, here is the center, and the diameter is along the x axis, the other diameter is along the y axis. So, let us calculate this. I x x is going to be integral y square d area. Since y is the same for this entire strip out here, which I am showing by purple color, I will take this area as dA, multiply by this distance y square, and then integrate. So, let us calculate the area dA. dA is nothing but this height of this strip, which is dy, times the length, and length is going to be square root of r square minus y square times 2. So, this is the area. All right. So, let me make it again to show it clearly. This is the semicircular thing. This distance is r, this is y, and therefore, this is r square minus y square. This entire distance becomes 2 times the square root of r square minus y square. And therefore, I x x is going to be 2 integral y square r square minus y square dy, and y varies from 0 to the radius r. This integral is easy to perform. I take y equals r sin theta, dy becomes r cosine of theta d theta, and therefore, I x x becomes equal to 2 integral lower limit theta would be 0, upper limit theta will be pi by 2, y square will be r square sine square theta, square root of r square minus y square will be r cosine of theta, and then you have dy, which is r cosine of theta d theta. Therefore, I can write this whole thing as I x x is equal to 2 r raised to 4 integral 0 to pi by 2 sine square theta cosine square theta d theta, which I can write as 2 r raised to 4 integral 0 to pi by 2 sine square 2 theta divided by 2 times 2 d theta. I made use of the fact that sine 2 theta is equal to 2 sine theta cosine of theta, and therefore, I x x becomes r raised to 4 divided by 2, because this cancels, 0 to pi by 2 times 0 to pi by 2 sine square 2 theta over d theta. Sine square 2 theta I can write as 1 minus cosine of 4 theta divided by 2. So, this becomes I x x becomes r raised to 4 divided by 4 integral 1 minus cosine of 4 theta d theta 0 to pi by 2. The second integral vanishes, this one vanishes. So, you get pi r raised to 4 by 8. Okay, that is the answer. How about the y axis? If I were to calculate this about this axis, y axis, I y y will be equal to integral x square dA. You could do it explicitly. I would immediately use a trick that this half of this whole thing, half of the semicircle, has moment of inertia is equal to pi r raised to 4 over 8, 1/2 of it, and so does the other one. But for a quarter, whether I take the moment of area about this axis or this axis is the same, and therefore, both the quarters, the one shown with orange and the other shown with green, have the same moment of area about the y axis, and therefore, this will become 2 times 1/2 pi r raised to 4 by 8, the same answer is pi r raised to 4 by 8. As the final example, I am now going to do a triangle, and to keep things simple, initially I am going to take a right angle triangle of height h and base b and calculate I x x, I y y and I x y for this. To calculate I x x, I again do integral y square dA, and this small area out here is this orange area, all right. I can make things simpler by taking, rather than this area, the entire strip out here, because y is the same for this entire strip, all right. Now, dA for this entire strip is going to be dy times its width, and the width is going to be at height y is going to be b times h minus y over h by similarity of triangles, because this height is y, this height therefore becomes h minus y, and this triangle is similar to the entire triangle. Therefore, I x x is equal to integral y square times b over h minus y dy, which is b over h times h, and y is varying from 0 to h. So, h cube over 3 minus y cubed integral, which will be h raised to 4 over 4, and this comes out to be b over h times h raised to 4 over 12, which is nothing but b h cubed over 12. So, I x x, that is the second moment of area about the x axis for this triangle, is b h cubed over 12. The same calculation can be repeated for calculation about the y axis, except in this case we will take the area to be like this, and I will leave that exercise for you to show that I y y would beautifully come out to be h b cubed over 12. It is exactly the same exercise. And finally, let us calculate I x y, which is nothing but integral x y dA. Now, in this case I have to be a little careful, because this integrand involves both x and y. I will take a small area here and write this as integral x dx y dy, or equivalently y dy x dx. You can perform one of the integrals to start with. Now, x integral, if I were to perform, notice that x integral over x in this strip is going to be from 0 to b h minus y over h up to this distance, and therefore, this integral becomes y dy. Y varies from 0 to height h, integral x varies from 0 to b h minus y over h x dx. That is the integral that we have to perform. So, let me box this. So, for a given y, x varies from here to here, which is 0 to b h minus y over h, and then y varies from 0 to h. And you calculate this, I will let you do the integral. This comes out to be b square h square over 24. So, for a right angle triangle, we just calculated, if its base is b and height is h, we have calculated that I x x comes out to be b h cubed over 12, I y y comes out to be h b cubed over 12, and I x y comes out to be b square h square over 24. So, obviously, x and y axes in this case are not the principal axes. If I were to find the principal axes, I would do a rotation by an angle alpha such that tangent to alpha is 2 b square h square over 24 over I y y, which is h b cube over 12, minus I x x, which is b h cubed over 12. So, this gives me b square h square over h b cubed minus b h cubed, which comes out to be b h over b square minus h square. So, if b is greater than h, alpha comes out to be greater than 0. If b is less than h, alpha comes out to be less than 0. These are the principal axes. One more comment is, if the triangle was not right angle but something like this, with total base size b, this being b1, this being b2, and height h, I x x will still come out to be b h cube over 12, because both these triangles, the one shaded and the other shaded by green, are right angle, and each one of them has the I x x, which is b1 h cube over 12, and the other one is b2 h cube over 12, and you add them and you get this answer. Thank you.